So hey guys, welcome to my channel. So in this video I'm going to explain this mother vertex. So the problem statement is we have given a directed graph, so we have to find the root of this graph, or we can say mother vertex of this graph if present. So mother vertex is the we can say vertex through which we can reach all the vertex of the graph. So let me explain this question with the help of this example. So we have to find the root of the, we can say, root of the graph. So let's say I have this graph. Let's say this is node 5, this is node 4, and this will be directed graph. So this will be the directed edge from 4 to 5, and this is node 0, this is node 1, this is node 2, this is node 3. So we have edge between 4 to 3, and this is from 5 to 0 and 0 to 1, 3 to 0 also an edge. We have also an edge from 2 to 3 and 1 to 2. So now we have to find the, we can say, mother edge or mother vertex. So we have to find the mother vertex, or we can say root vertex. We can say root vertex. So root, so let me explain first. So let me first explain this, what is root. Root, that is root vertex. So root vertex is the vertex from which which we can go in every all the nodes are reachable to that node. For example, let's say in this case 4. So you can see that from 4 each of the node are reachable from the 4. So this let's say I have this vertex 4. So from 4 I can go any of the vertex. For example, if I want to go this node 2, that is vertex 2, then I can go easily. So there are two parts available. So first part will be 4 to 5, 5 to 0, 0 to 1, and 1 to 2, and second part will be, that is from 4 to 3 and 3 to 0, 0 to 1, 1 to 3. Okay, 1 to 2. So so in simple terms we can say root node, or we can say mother vertex is a vertex from where we can go all the nodes are reachable from there. That is called the we can say mother vertex. So how we can find this mother vertex? So the first simple approach which comes in our mind is we can do simply DFS traversal. We can simply do DFS traversal if and we will take an visited array which will keep track of our unvisited nodes. Initially we will simply uh, set all the vertices at as we can say unreachable. That means we will set all the visited nodes false. So there are we can say 5 okay, six nodes. So size of the visited array will be 6, that is 1 2 3 4 5 and 6. Okay, so let me do the indexing of this visited array, that is 1 2 3 4 5 6 4 5. So our indexes start from 0, that will be goes from 0 to 5. So we have 6 nodes. So if I make a DFS call from this node 0, then I will explore the neighbors of the 0. Then the neighbors of the zeros will be from 0 I can go to only node 1. So from 1 also, if I make the DFS call, that will go to from 1 also we can go to node 2, and node 2 we can go to node 3, and node 3 node from node 3 we can go node 0, but node 0 is already visited. So my DFS will stop here. Okay, so simple, we can say simple approach will be, we have to, we can say, call all the, or we can say we have to, do DFS call to every node. And if this condition is, we can say, if my all the nodes are visited from that particular, we can say, by calling the DFS from that particular node, so that particular node will be the, my this, we can say, my root node. That node will be my root node. So all the nodes that all the nodes should be reachable from that particular node. And that node can be called the, we can say, parent node or root node. So the simple approach will be, we will simply, what we will do, we will simply make the call, make the DFS calls for all the nodes. And the node that, if my visit, and the, that DFS call, that will visit my whole visited array, that will visit, we can say, that will mark true to my all visited array, that will be my the, this parent, or we can say root node. So simply what I will do, I will simply uh, make the DFS calls from the each node. So simply, let's say, if I make the DFS call from 4, so DFS of 4, so from 4 there are two paths available. The one first path will be, from 4 we can go to node 5 and node 3. So this will be node 5, DFS of 5 will be called, and here DFS of 3 will be called. So there are two paths available, in the, we can say, two paths available for the, we can say, two neighbors are available for the node 4. And from node 4 we can go to node 5 and node 3. And from node 5 we can go to node 0, and then 1, and then 2, and then 3. 3 will be already visited, so we don't have to explore it again. So we don't have to go again there. So what we, so by hitting the DFS at node 4, it will, what it will do, it will mark all the, we can say, nodes visited. So that's our requirement. So we will store this, we can say, store the value of this node, that will, and we will store the value of this node, that is 4, and return this 4. So that will be our final output. So this is the simple logic. So for this, we can say brute force approach, or this will be the brute force approach, or let's we can say discuss the time complexity for this approach. So we will, what we will do, we will we will try to make call, for every, we will try to make DFS calls for every node. So we have, let's say we have n nodes, let's say we have v vertices and e edges. Okay, so the time complexity will be big O of, that is, as we are, we can say, going, we can say, making DSF calls for all the nodes. So the time complexity of DFS will be big O of, that is v plus e, because we are visiting the that, edge of that particular node also. So that, here v is the vertex of the graph. So v is representing the vertex of the graph, and e is representing the edge of the graph. So because we have to find the, we can say, edge, or we can say find the neighbors, so this will be the edge of the graph, so this will be the vertex, and this will be the time complexity. And space complexity also will be the big O of n, because we are calling the DFS in the we can say recursive stack. We so we are calling the DSF function in the recursive stack, so that space complexity will be, that is big of v, that is v stands for the vertex of the graph. So if I have v vertexes, so the space complexity will be big O of v. So what will be the another approach for this, we can say, for this problem, what will be the another approach? So another approach will be, we can say, we can think of the, that is, okay, we have to simply we have to visit every node once. So we have uh, so one simple approach is coming into my mind is, we do not need any duplicate, we can say duplicate node, so we can make use of set. So set is the we can say data structure in C++. Set will the data structure in C++, set will contain the only, you can say, unique element. Set will contain only unique element, it does not contain any it cannot contain any we can say duplicate element. So if I have visited nodes at once, so it will contain so it will contain only the unique nodes, and we will. So here what we are doing here is, in previous approach we are making this DFS unnecessary DFS calls. So these DSF calls can be reduced with the help of the this data structure, that is set. What we will do, set is a data structure that will contain only the unique nodes. So this set data structure will contain only the unique element. So in our case we need the only we have to reach the every element at once, or we can say every nodes or vertex at once. So we need this data structure that will keep, we can say, keep track of our unique visited vertexes. So this data structure will store the unique, we can say unique unique vertex of the our graph. So this will reduce the our this DFS nodes, sorry, DFS calls. So let's we will make the DFS calls if our that element if if we are visiting that node first time. So we will simply do the DFS calls if our that node will be visiting the first time, if we are visiting that node at first time. So after that we will after that only we are going to make that this DFS call. So that will be the our brute force, sorry, optimized approach. So what we will do, simply in this case, let's say I am starting from this 0th node. So let me write the adjacency list of this I can say this graph. So node 0, from node 0 where I can go, from node 0 I can go only to node 1, only node 1, and from node 1 I can go to node 2, only node 2, and from node 2 I can go to node 3 only, and node 3, and from node 3 I can go to node 0, and from node 4 I can go to node 5 and node 3, node 5 and node 3, and from node 5 I can go to node 0 only. So what I will do, I will simply iterate from 0 to, that is number of vertices. So first I will this I will make call DFS call from node 0. That will simply first it will mark visited, then it I will explore the neighbors of the, we can say, and I will insert this 0 into my set, and what I will do, I will simply explore explore the, what I can say, explore the neighbors of the 0. So neighbors of the 0 are 1. So 1 will be inserted and mark true here. 1 will be inserted into my set, and mark visited, and neighbors of this 2, 1 will be 2, and this will be marked visited, and 2 will be here, and this will be 2 to 3, that will be also my, okay, that will be also marked visited, okay. Then 3 to 0, that will be we can say, we will not visit that, because we have 0 already into my set, so I will not make any DFS calls. So after that, what I will do, I will refresh my this set and make the another call. So for one also there will be this whole we can say will be mark visited, and let's say I am doing the DFS call from node 4. Then what I will do, first of all I will mark visit to node 4 will be marked visited, and it will explore the neighbors of this, that will be node 5. Node 5 will be marked as visited. So all the all the, we can say, all the neighbors of the 4 are come into my set, and that will be that is 0. My set will be look like that, look like this, that is 0 1 0 1 2 3 4 and 5, okay. And this size of my this set will be equal to the number of our given nodes. So s dot size, let's say this set name is s, so s dot size is equal to our, that is equal to our vertex. If this is true, then we have to return that node. If the size of the set is coming to equal to the our vertex, given vertexes, then I have to return that node. So that node will be the our parent or root node. So this will be also another approach. So in the previous approach, what I have not explained is simply after making calls from each nodes, DFS calls from each nodes, we have to recheck our that particular node, and we have to simply what I can say, simply mark my visited array to false, and check if my that possible if my that possible that I am what I can say, uh, if that my possible if my that possible indexes that is coming, we can say, if I have to make ensure that if I call that indexes and make DFS calls from that node, that particular node, so it should be reachable to all nodes. So in previous we can say previous approach, what I have explained is I have explained that we have to make calls from the every node, okay. And if I am reachable to every node from that particular node, so that particular node will be my answer. So that might be not our answer, so we have to recheck that. So how we can recheck that? So I will simply make my visited array to unvisited, that is visited array. I will simply mark all the my visited nodes to unvisited, and simply make DFS calls from that particular node. But let's say the answer is my answer is coming to 4, so I will make the DFS calls from node 4. And if I am reachable to, I am visiting all the nodes and I am reachable to all the, we can say, all possible nodes, so that is my correct answer. If I yeah, if I am reachable to all the nodes, that will be my correct answer. If I am not reachable to that, we can say, if I am not reachable to all the nodes, that means my answer will, I don't have any answer, and that will, I don't have any parent vector, or sorry, parent node, so I have to return the -1. So in question we have given that uh, there might be a possible case that that graph cannot be, we can say, cannot contain any parent vector, sorry, parent, I can say parent vertex, or we can say root vertex. So it might be happen, so we will I have to take the corner, we can say, worst scenario. In the worst scenario, it can we cannot have the parent vector, sorry, parent, or we can say parent root, so, or we can say mother vertex. So we have to recheck again, we have to recheck again. So let me explain with the help of the code. So what we are doing here is simply, so the first loop will be iterating through the all vertices and perform the DFS starting from the unvisited vertices, and it will, we can say, it will set our possible to a particular node, and after that I have to cross check that particular node is reachable to all the nodes. So I will make the DFS call again. Okay, and if my any vertex is unvisited, so I will return -1. So means that there is no parent or mother vertex present in that graph, and the time the time complexity will be simply big of e plus e. I have explained this, and v here, v stands for the vertex of the graph, and stands for the edges of the graph. So e is representing the edge of the graph. So and time complexity will be big of v, that is vertex. So because we are what we are calling the VSF, so in the recursion stack, so VSF will take the that is big of v, that will be v here is representing the number of vertex. So that's all for this question. So I hope you will get the logic behind this question. This question is very very easy. So let me meet in the next meetings. Till then, bye bye, take care.